The universe begins with the Big Bang, a moment of explosive expansion that marks the beginning of time itself. In an instant, all the matter and energy that would form the universe is concentrated into an infinitesimally small point, an infinitely dense singularity, which then bursts outward in a rapid and unimaginable expansion. This expansion, known as cosmic inflation, occurs within the first fraction of a second setting, the stage for the universe to evolve. As the universe expands, space itself stretches, and the tiny dense point transforms into a vast, rapidly cooling cosmos. The laws of physics as we understand them today do not yet apply at this moment, and the conditions that follow radiation energy and the formation of basic elements are the foundation upon which everything else will rest. The temperature during this time is so high that matter exists as a quark-gluon plasma, with particles in an extreme state of agitation. There is no distinct separation between particles or forces. All are unified in this early chaotic state. This sudden burst of expansion continues to define the structure of the universe to this day. Within a mere few moments after the Big Bang, as the cosmos cools, the first fundamental particles begin to form quarks, electrons and neutrinos. As the universe cools further, quarks combine to form protons and neutrons. These particles then begin to combine and form the simplest elements, hydrogen and helium. The first atoms are created as the universe cools enough for electrons to be captured by nuclei. These atoms are the building blocks of all matter that will follow. However, this process of cosmic formation occurs against a backdrop of rapid expansion space itself, stretching at a rate far beyond the speed of light. The universe, though still hot and dense, becomes a vast and spreading expanse filled with energy light and the building blocks for all future structures. In this early phase of the universe, the laws of physics are still in the process of taking form. Gravity, electromagnetism, and the strong and weak nuclear forces emerge from a singular energy state, slowly differentiating into the distinct forces that govern the interactions between particles. Though the exact details of this transition are still uncertain, it is understood that in this brief fiery moment, the universe begins to evolve into something recognizable, one governed by the forces and particles we experience today. The early universe is a state of energy, light and temperature so extreme that even the forces we know are not fully separated. The fundamental particles of the universe are still being shaped, but even within these first seconds, the structure of the cosmos is set into motion. Though the universe is still largely opaque with light unable to travel freely through the dense plasma of particles, it is also a universe in flux, undergoing rapid and dramatic changes. The intense energy begins to dissipate, and as the universe continues to cool, a new era begins. Space, once filled with a hot, dense soup of particles, becomes increasingly sparse with regions forming that will eventually become the galaxy's stars and planets. It is during this time, just a few minutes after the Big Bang, that the first nuclei form. The universe, though still in its infancy, begins to lay the foundations for everything that will come. As time passes, the cooling continues and the universe transforms from an opaque and featureless expanse into a cosmos full of structures, some large, some small, all interconnected in a web of cosmic evolution. The Big Bang then represents not just the birth of matter, but the birth of time itself, the beginning of everything. The rapid expansion that follows the cooling and the gradual formation of particles, atoms, and elements mark the beginning of the universe's long journey toward complexity. Yet at this stage, the universe is still in a state of flux. The forces of nature are not fully separated, and the laws governing them are still in the process of taking shape. This early phase, which lasts only a few moments, sets the stage for everything that will come later, but it also marks the end of the most extreme conditions the universe will ever experience. The energy of the Big Bang is still present, but as the universe cools, it becomes more stable, and the vast expanding expanse begins to evolve toward the formation of structures, galaxies, and stars. This era, known as the Cosmic Dawn, marks the beginning of the universe's evolution from chaos to order. From this point onward, the universe will continue to evolve, governed by the forces of gravity, electromagnetism, and nuclear forces. These forces will shape everything from the formation of the first stars to the eventual death of the universe. But for now, in the aftermath of the Big Bang, the universe is in a delicate state, just beginning to cool and evolve. The early moments are pivotal in setting the course of cosmic evolution, and everything that follows will be shaped by these first moments of expansion, cooling, and formation. As the universe continues to cool and expand, it begins to take on more recognizable structures. The matter created in these early moments of the Big Bang coalesces into galaxies, stars, and planets, marking the gradual transition from the chaos of creation to the ordered complexity of the cosmos we observe today. While the details of this transition are still unfolding, it is clear that the early universe laid the foundation for everything we see, from the smallest particles to the largest galaxies. And though we cannot see these early moments directly, the cosmic background radiation, the remnants of the Big Bang, serves as a glimpse into the past, offering scientists a window into the birth of the universe and the forces that shaped it. In this way, the universe continues to unfold from its first moments. The beginning of time, the rapid expansion, the cooling, and the creation of the first particles and atoms all mark the start of an expansive journey. A journey that will stretch across billions of years as the universe grows, cools, and evolves, shaped by the forces of nature that emerged from the singularity of the Big Bang. From the birth of the universe to its eventual end, every moment will be shaped by the interplay between gravity energy and the fundamental particles that arose from this moment of cosmic creation. And while the universe's fate may be uncertain, its beginning is clear, a moment of expansion, cooling, and the first hints of the complexity that would one day emerge. As the universe continues to expand, galaxies, stars, and cosmic structures begin to form, but the process is slow, taking millions to billions of years. The universe in its early stages is a vast cooling expanse, filled with a primordial mix of hydrogen and helium gas. The fabric of space is stretching constantly, pushing galaxies farther apart from each other. During the first few 100 million years after the Big Bang, the universe remains largely opaque. The photons or particles of light are scattered by free electrons and atoms, preventing them from travelling freely. This era, known as the Cosmic Dark Ages, is a time of quiet expansion, where nothing is visible except the dense, hot background radiation that still lingers from the early stages of the universe. Over time, as the universe continues to cool, regions of matter begin to condense under the influence of gravity. The gas, primarily hydrogen and helium, gathers into clumps which eventually form the first stars and galaxies. These clumps of gas, initially dense and hot, collapse under their own gravity, causing the gas to heat up and ignite nuclear fusion, marking the birth of the first stars. These stars, formed within the first few 100 million years of the universe's life, are massive and short-lived, burning through their fuel rapidly and casting their light into the vast dark expanse of the cosmos. Their formation is a key event in the universe's early history, for it marks the first organized structures, the first lights in the universe's dark, cold void. The formation of the first galaxies soon follows as the gravitational pull of the newly formed stars attracts more gas and matter, causing it to collapse into larger, more complex structures. These early galaxies are small, irregular, and chaotic, in contrast to the spiral and elliptical galaxies that we observe today. Their stars are densely packed, and they burn hot and bright, fueling the formation of even more stars, while at the same time giving off enormous amounts of radiation. This radiation begins to ionize the surrounding gas, allowing light to travel freely across the expanding universe. The cosmic dark ages are brought to an end, and the universe becomes transparent to light, revealing the first visible structures in the cosmos. This period, known as reionization, is the transition from a dark, opaque universe to one that is lit and observable, laying the foundation for the formation of galaxies and large-scale cosmic structures. As the universe continues to expand and cool, galaxies grow larger and more complex structures begin to form. The gravitational pull between galaxies causes them to collide and merge, forming clusters of galaxies and vast cosmic superstructures. These galaxies evolve over billions of years, with some forming spiral arms, while others develop into elliptical shapes or irregular structures. Stars are born and die within these galaxies, creating elements heavier than hydrogen and helium, which are eventually spread across space when massive stars explode in supernova. These elements, such as carbon, oxygen, and iron, are the building blocks for life as we know it. They are the very ingredients that form planets, stars, and life itself. But even as galaxies continue to grow and evolve, they are still part of an expanding universe. The fabric of space continues to stretch, causing galaxies to move farther apart from each other, a process that will continue indefinitely. Despite the ongoing expansion, some galaxies are drawn together by gravity, forming clusters and superclusters. These massive structures are the largest known objects in the universe, with galaxies bound together in groups that can contain hundreds or even thousands of individual galaxies. In the center of many galaxy clusters, supermassive black holes reside, their gravity so intense that they influence the movement of galaxies within the cluster. These black holes can pull in large amounts of gas and dust, forming accretion disks that radiate immense amounts of energy. The presence of black holes, along with the expansion of space, ensures that the universe is a dynamic and ever-changing place, with galaxies and their stars constantly evolving, colliding and merging while space itself continues to stretch outward. The forces that govern the universe, the gravitational pull of massive objects, the expansion of space itself, and the electromagnetic forces that hold atoms and molecules together, interact in complex and fascinating ways, creating the intricate tapestry of the universe. Yet even as the universe continues to expand and evolve, it is also subject to the fundamental laws of physics, which dictate the flow of time and the eventual fate of cosmic structures. The expansion of the universe, which began with the Big Bang, continues to this day, but over time it will begin to slow down, eventually reaching a point where the rate of expansion no longer accelerates. The future of the universe, while uncertain, is deeply intertwined with this expansion, which has profound implications for its ultimate fate. Whether the universe continues to expand forever, eventually slowing and collapsing in on itself, or whether it reaches a state of stability, where the forces of gravity and expansion balance out, remains one of the great unanswered questions in modern cosmology. As time progresses, the galaxies, stars, and planets that populate the universe will continue to evolve. Stars will burn through their fuel, some exploding in brilliant supernovae, others quietly fading into white dwarfs or neutron stars. Galaxies will collide and merge, creating new stars and systems in the process. The elements necessary for life will be spread across the universe, enriching future generations of stars and planets. The cosmos will continue to evolve, but it will eventually reach an end that is still millions to billions of years away. The question of how the universe will die remains at the forefront of modern science, with many potential scenarios to consider. Some scientists suggest that the universe will continue to expand forever, gradually cooling and fading into a state of entropy known as the heat death of the universe. Others propose that the expansion will slow and reverse, eventually causing the universe to collapse in a big crunch. Still others speculate that the universe will experience a big rip, where the expansion accelerates to the point that galaxies, stars, and even atoms are torn apart. The fate of the universe remains uncertain, but one thing is clear: the universe, like all things, will eventually come to an end. Cosmic inflation, the rapid and extreme expansion of the universe in its earliest moments, marks one of the most profound shifts in the evolution of the cosmos. This period of inflation occurs just after the Big Bang, lasting only a fraction of a second, but having lasting consequences for the structure of the universe. During this time, the universe expands exponentially, far faster than the speed of light, stretching the very fabric of space itself. The result is that the observable universe we see today is vast beyond comprehension, with regions of space far removed from each other, yet linked by the same origin. The rapid inflation smoothed out irregularities in the early universe, creating a homogeneity that continues to define the large-scale structure of the cosmos. After this initial burst, the universe continues to expand, but at a much slower rate, setting the stage for the formation of the first structures such as galaxies and stars. This expansion would have also cooled the universe dramatically from the extreme temperatures of the early Big Bang to a more temperate state, allowing for the formation of atoms and the birth of light itself. However, inflation also creates a profound question about the ultimate fate of the universe. The inflationary period sets in motion the processes that will shape the universe's structure for billions of years to come, but it also leads to a paradox. The universe expands so quickly that it appears to be in a state of perpetual growth, pushing galaxies, stars, and planets further and further apart. Over time, the rate of expansion accelerates as dark energy begins to take effect, pushing the boundaries of the cosmos further outward at an increasing rate. This cosmic acceleration, though a natural consequence of the universe's expansion, raises the question, will this expansion continue indefinitely? The universe, though, seemingly vast and eternal, may eventually reach a point where the forces that drive its growth will lead to an ultimate end. Whether this expansion slows down and eventually reverses or continues to accelerate depends on the interplay between the universe's various forces. As the universe expands, the large-scale structure of galaxies begins to form. These structures are not distributed randomly, but instead emerge in patterns dictated by the interplay of gravity, dark matter, and other forces. Gravity, the force that attracts objects with mass towards one another, causes matter to clump together, forming the first stars and galaxies. These early galaxies, formed from clouds of hydrogen and helium gas, are simple and unstable. Over time, as more stars form and gravity causes galaxies to collide and merge, these structures evolve into the complex cosmic arrangements that we observe today. Galaxies form clusters, and these clusters in turn form superclusters, creating the intricate web-like structure that defines the large-scale organization of the universe. Within these galaxies, stars are born live and die, creating the elements that are necessary for the formation of planets and life. The light from these stars shining through the vast emptiness of space allows us to observe the history of the universe, providing a window into its past and helping us understand the forces that shape its future. Though galaxies and stars form and evolve, the universe's expansion remains a dominant force. The space between galaxies stretches, causing galaxies to move away from each other. This expansion continues to accelerate as dark energy, an unknown force that opposes the gravitational pull of matter, becomes increasingly influential. The discovery of dark energy, one of the most profound revelations of modern cosmology, has shown that the universe's expansion is not slowing down as once expected, but instead is accelerating. This accelerating expansion is a key factor in the ultimate fate of the universe. If dark energy continues to drive this acceleration, the universe may eventually reach a state where galaxies, stars, and even individual atoms are torn apart. This scenario, known as the Big Rip, suggests that the very fabric of the universe could unravel, driven by the force of dark energy. While this is still a subject of study and debate, it remains one of the potential outcomes for the universe's future. In the early universe, gravity was the dominant force bringing matter together and causing the formation of stars and galaxies. However, as the universe expands, gravity becomes less effective at holding large structures together. The space between galaxies continues to stretch, and the gravitational pull between galaxies weakens, allowing them to drift apart. This expansion, while initially slow, accelerates as the influence of dark energy becomes more pronounced. The continued acceleration of the universe's expansion could result in a future where galaxies move farther apart at an ever-increasing rate, making the universe appear emptier and darker. Stars will continue to burn out and die, and new stars will form more slowly, creating a universe that becomes increasingly inhospitable to life as we know it. The eventual death of stars, the cooling of remnants into white dwarfs and black holes, and the fading of light will mark the end of the vibrant dynamic universe we see today. The expansion of the universe is an ongoing process that will continue for billions of years to come, but it is one that holds profound consequences for the universe's future. As galaxies drift further apart, the universe will become more isolated and dark. Stars will burn out and their remnants will drift through the cold, dark void of space. The energy that once fueled the universe's growth will dissipate, leaving behind a universe that is cold, empty and dark, a universe in which the last remnants of matter slowly fade away. The fate of the universe, though uncertain, is ultimately tied to the expansion that began with the Big Bang. Whether the universe continues to expand indefinitely, eventually slowing and contracting, or whether it reaches a state of stability or even collapse remains one of the key questions in cosmology. As we look toward the future, the fate of the universe will be determined by the forces that drive its expansion and the interactions between dark energy, gravity, and the matter that fills it. The continued expansion of the universe suggests that one day, everything we know, the galaxies, the stars, the planets, and the very atoms that make up matter will be scattered across an ever-widening void. The universe, once filled with light and energy, will fade into darkness, a process that will take place over billions of years. This gradual decline, driven by the forces of expansion and entropy, will mark the slow, inevitable end of everything. Yet the universe's fate, though inevitable, is still a distant event. There are billions of years left before the forces that govern the universe lead to its demise. Stars will continue to burn, galaxies will continue to evolve, and the vast reaches of space will continue to stretch outward. The forces of nature will continue to shape the cosmos, and new discoveries will be made about the structure of the universe and its future. But the end is already set in motion, and the eventual fate of the universe, while still far off, is already written in the stars. As the universe continues to expand, the forces shaping its evolution become more pronounced. With galaxies, stars, and cosmic structures beginning to emerge, the universe enters a new phase where the interplay between gravity and the expansion of space creates the fundamental patterns we see today. The formation of galaxies is one of the first and most significant milestones in this phase. Gravity, the force that binds matter together, works on every scale, from the clumping of gas clouds to the formation of galaxies and clusters of galaxies. In the early universe, hydrogen and helium atoms formed shortly after the Big Bang are scattered across vast distances. These atoms, while simple, are the building blocks of everything else. Slowly, under the influence of gravity, the matter in the universe begins to coalesce into larger structures. Regions of higher density attract more gas and matter, pulling them together over time, eventually forming stars and galaxies. Stars are the next major feature in the universe's structure. Their formation marks a key moment in the life of the cosmos. As regions of gas collapse under the influence of gravity, the temperature and pressure rise, leading to nuclear fusion. Hydrogen atoms fuse into helium, releasing energy and light, which we observe as starlight. These first stars, known as population 3 stars, are incredibly massive and hot. They burn through their fuel quickly, living short, intense lives. Their deaths of violent, massive stars end their lives in supernovae explosions that scatter heavy elements into space. These elements, carbon, oxygen, nitrogen, are the building blocks for planets, and eventually life. Over time, these stars give way to second and third generations of stars with lower mass and longer lifespans, and galaxies begin to take shape around them. The formation of galaxies marks another critical point in the universe's evolution. Galaxies are collections of stars, gas and dust bound together by gravity. The first galaxies are small, irregular in shape, and chaotic, often colliding with one another as they grow. Over billions of years, these galaxies will evolve into the more stable, structured galaxies we see today, with spiral, elliptical, and irregular forms. Galaxies are not isolated in space. They form groups, clusters, and superclusters, interconnected by the force of gravity. Galaxies and clusters can interact, collide, and merge, and their stars are often influenced by these interactions. Despite the complexity of galaxy formation, the universe continues to expand. The expansion which began with the Big Bang continues to this day. The space between galaxies stretches, causing them to move away from each other. This expansion is not uniform. It happens at different rates in different parts of the universe depending on the distribution of matter and dark energy. The discovery of dark energy, a mysterious force that is driving the accelerated expansion of the universe, has added a new layer of complexity to our understanding of cosmic evolution. Dark energy, which makes up about 70% of the total energy density of the universe, works against gravity pushing galaxies apart. The exact nature of dark energy remains one of the greatest unsolved mysteries in cosmology. As galaxies continue to expand and evolve, the fate of the universe becomes increasingly tied to this expansion. The accelerated expansion driven by dark energy suggests that the universe may continue to grow indefinitely. If this expansion continues unchecked, the space between galaxies will increase, and galaxies will become increasingly isolated. As galaxies drift apart, stars will burn through their fuel and die, leaving behind remnants like white dwarfs, neutron stars, and black holes. The gas and dust that once formed stars will be spread thin across the universe, and new stars will form less frequently. Over time, the universe will become increasingly dark as the light from stars fades, and the remnants of cosmic structures are scattered across an ever-expanding void. However, the continued expansion of the universe is not without consequences. As space stretches, the energy in the universe is spread more thinly, and the temperature of the cosmos begins to decrease. The heat death of the universe, a possible scenario for its end, occurs as entropy disorder continues to increase. Over time, stars burn out, galaxies drift apart, and the universe approaches a state where no usable energy remains. The universe will continue to expand, but as it does, the energy available for work decreases, leading to a cold, dark, and desolate cosmos. This scenario, known as the heat death, is one of the most widely accepted predictions for the ultimate fate of the universe. At the same time, black holes which form from the collapse of massive stars continue to influence the universe's evolution. Black holes are regions of space where gravity is so intense that nothing, not even light, can escape. As black holes grow by consuming gas and stars, they become even more powerful, and their influence spreads across the cosmos. At the center of many galaxies, including our own Milky Way, supermassive black holes reside their gravitational pull, affecting the movement of entire galaxies. But even black holes are not immune to the passage of time. Over extremely long timescales, they slowly evaporate through a process known as Hawking radiation, a quantum phenomenon in which black holes lose mass and energy. The ultimate fate of black holes is still uncertain, but if the universe continues to expand, they too will eventually vanish, leaving behind only a thin, cold remnant of the universe's once vibrant activity. The continued expansion of the universe will also affect the formation of new structures. As galaxies move farther apart, the material needed to form new stars becomes increasingly sparse. New galaxies may still form, but they will be isolated, separated from the larger structures of the universe. The formation of stars will slow, and over billions of years, the universe will enter a period of decline. The most massive stars will have burned out, leaving behind black holes and other remnants. Eventually, all the galaxies will be isolated from each other, and the universe will be a dark, cold place filled only with the remnants of the stars that once illuminated it. This end will unfold over an incredibly long time, but it represents one of the most likely scenarios for the fate of the universe. The universe will not end in a dramatic explosion, but rather in a gradual, silent fade into emptiness, where the last traces of energy are slowly used up, leaving behind only a vast, dark void. As the universe cools and expands, entropy continues to increase, and the cosmos becomes a place of stillness. The stars that once lit the sky will fade into darkness, and the remnants of galaxies will drift apart. Black holes will eventually evaporate, leaving no trace behind. The universe in its final moments will be a place of darkness devoid of stars, galaxies, and life. Yet this end, though inevitable, will not happen for billions, if not trillions of years. The universe will continue to evolve, and stars will continue to form and die, but eventually it will reach a point where all activity ceases. In this distant future, the universe will be cold, dark, and devoid of energy, a silent remnant of the vibrant cosmos we observe today. The fate of stars plays a pivotal role in determining the long-term evolution of the universe. As the cosmos expands and galaxies evolve, stars continue to form, burn through their fuel, and eventually die. The life cycle of a star is determined by its mass, with more massive stars burning through their fuel much more quickly than smaller stars. The most massive stars, which are hundreds of times heavier than our Sun, live short, intense lives. They burn brightly, fusing hydrogen into helium in their cores, but eventually exhaust their fuel, causing them to collapse inward under the force of gravity. This collapse results in a dramatic explosion known as a supernova, which can briefly outshine an entire galaxy. The remnants of the explosion, including heavy elements like iron, are scattered into space, enriching the surrounding gas and dust, and providing the material for the formation of new stars, planets, and even life itself. Smaller stars like our Sun follow a different path. They burn more slowly, lasting billions of years. As they approach the end of their life, they begin to expand into red giants, their outer layers puffing up and engulfing nearby planets, including Earth. Eventually, these stars shed their outer layers, creating a nebula of gas and dust, while the core contracts into a dense white dwarf. White dwarfs are small, but incredibly dense, and they slowly cool over billions of years. While they may remain intact for trillions of years, they will eventually fade into a cold, dark remnant no longer capable of supporting life or activity. The death of stars, particularly massive ones, is a significant event in the evolution of the universe. Supernovae are responsible for the creation of many of the elements heavier than hydrogen, and helium elements like carbon, oxygen, and iron. These elements are the building blocks for planets, stars, and life itself. Without the death of stars, the universe would lack the complex materials necessary for the formation of the structures that make up our world. In this way, the end of a star's life is inextricably linked to the beginning of new forms of matter and energy. The death of stars, while marking the end of one phase of the universe's life, also paves the way for the next stage, enriching the cosmic environment and setting the stage for the formation of new stars, planets, and galaxies. However, as time progresses and the universe expands, the process of star formation slows. The gas needed to form new stars becomes more diluted, and the remaining fuel in the universe is spread thin across vast distances. As galaxies continue to expand and move farther apart, the rate of star formation decreases and fewer new stars are born. Eventually, the remaining gas in the universe will be consumed, and the formation of new stars will come to an end. The universe will be left with only the remnants of the stars that have already burned out. White dwarfs, neutron stars, and black holes will be the only structures remaining in the universe, and the cosmos will slowly grow colder and darker as energy is spread thinner and thinner. In the distant future, the most massive black holes will continue to grow by accreting matter from the surrounding space. These supermassive black holes, which reside at the centers of galaxies, will continue to exert a powerful gravitational pull on their surroundings, influencing the motion of entire galaxies. However, even black holes are not immune to the passage of time. Over incredibly long periods, black holes are predicted to slowly lose mass through a process known as Hawking radiation. This phenomenon, predicted by physicist Stephen Hawking, involves the emission of radiation from the event horizon of a black hole. Over billions or even trillions of years, this process could cause black holes to lose mass and eventually evaporate, leaving behind only a faint trace of their existence. The evaporation of black holes marks another stage in the death of the universe. As the last black holes slowly fade away, the universe will become increasingly empty, with only the faintest remnants of its once vibrant past remaining. Stars which once shone brightly and created the elements necessary for life will have burned out and collapsed into dense remnants. Galaxies will be scattered across an ever-expanding void, unable to interact with one another due to the vast distances between them. The universe once filled with light and energy will become dark and cold, with no stars or galaxies to illuminate the vast emptiness. The eventual disappearance of all matter, the fading of light, and the cooling of the universe will mark the final stages of cosmic evolution. As the universe approaches this state, the forces of gravity, electromagnetism, and nuclear forces will have all but ceased to influence the universe's behavior. The universe will be a cold, dark, and lifeless expanse, devoid of the energy and activity that once defined it. The entropy of the universe will continue to increase as energy is gradually dissipated and all matter becomes more evenly distributed. The ultimate fate of the universe as it reaches this final state will be one of stillness and quiet, with no processes of change or activity to disturb its calm. This eventual fate, often referred to as the heat death of the universe, is based on the second law of thermodynamics, which states that in any closed system, entropy will always increase. Over time, as stars burn out and black holes evaporate, the energy available for work will be spread so thin that no meaningful processes can occur. The universe will become a place of absolute entropy, with all matter in a state of maximum disorder. No stars will shine, no planets will form, and no life will exist. The universe will be a vast, empty and cold place with nothing but the faintest radiation lingering in the dark. The heat death of the universe represents one possible end to the cosmos, a slow and inevitable process driven by the expansion of space and the increasing entropy of the universe. While this is one of the most widely accepted scenarios for the future of the universe, it is not the only possibility. Other models, such as the Big Crunch or the Big Rip, propose different endings for the universe, each with its own set of consequences for the fate of galaxies, stars, and life. Regardless of the exact path the universe takes, however, it is clear that the universe's current state of rapid expansion and star formation will eventually come to an end. The universe will eventually reach a state of stillness, where no new stars will form, no galaxies will collide, and no matter or energy will remain to drive the processes of cosmic evolution. The end of stars, black holes and galaxies will be a slow process that unfolds over billions of years, but the ultimate result will be a cold, dark and empty universe, where the last traces of activity fade away, leaving nothing but the remnants of what once was. The death of the universe, though distant in the future, is a fundamental aspect of its evolution, one that will occur as a result of the forces and processes that have shaped the cosmos from the very beginning. The expanding universe and the forces shaping it are integral to understanding how the universe will ultimately end. As the universe continues to stretch, driven by dark energy, the galaxies that populate it grow farther apart. This expansion, initially thought to be slowing, was found to be accelerating in the late 20th century, thanks to observations of distant supernovae and the discovery of dark energy, a mysterious force that counteracts gravity. This acceleration means that the universe will never slow down or stop expanding. Instead, it will continue to grow with the fabric of space itself, stretching and carrying galaxies, stars, and other cosmic structures farther from one another. The consequences of this ongoing expansion are profound. As galaxies move away from each other, the space between them grows larger, and eventually they will be so far apart that they will become isolated from one another. The increase in the universe's size and the stretching of space brings with it the inevitable fading of cosmic light. As galaxies recede from one another, their light becomes red-shifted, meaning it moves toward the red end of the spectrum, losing energy as it does. This process causes the light emitted by distant galaxies to become fainter, and eventually it will be impossible to observe galaxies at all. Stars too will burn out over time. As the fuel they rely on is consumed, they either become white dwarfs, neutron stars, or collapse into black holes. The energy required to form new stars will dwindle as the supply of interstellar gas becomes more sparse, leaving behind a cold, dark, and nearly empty universe. The ongoing expansion of space, coupled with the death of stars and the dimming of light, marks the gradual decline of the universe into a state of absolute stillness. During the era of cosmic acceleration, as galaxies move further apart, it becomes clear that the universe is not only growing larger, but it is also becoming increasingly isolated. Once the galaxies drift far enough apart, they will no longer be able to interact gravitationally. The stars within each galaxy will continue to burn their fuel, but they will be left in isolation without any means of forming new stars, as the supply of gas for star formation becomes increasingly scarce. Over the course of billions of years, the last remaining stars will burn out and the cosmos will be left with remnants of dead stars, black holes, and cold, dark regions of space. The universe will have entered its final dark stage where energy is so spread out and entropy so high that nothing will be able to sustain any activity. The increase in entropy is a key factor in the eventual heat death of the universe. Entropy, the measure of disorder in a system, continues to rise as energy becomes more uniformly spread throughout the cosmos. In this state of maximum entropy, no usable energy will remain, and all physical processes that rely on energy transfer will cease. The universe will reach a point where no stars shine, no new stars are born, and no meaningful processes occur. Matter once formed into stars and galaxies will eventually be spread so thin across the expanding universe that it will no longer be able to sustain itself. Black holes, the last remaining sources of intense gravitational pull, will eventually evaporate through Hawking radiation, releasing their mass over incredibly long periods. This will leave behind only the most basic particles scattered across an empty universe. As the universe grows colder and darker, it will approach the ultimate limit of its existence, one in which no more energy can be extracted from its physical systems. In this state of near-perfect entropy, life as we understand it will be impossible. The temperature will approach absolute zero, and any remaining radiation from dead stars or evaporating black holes will become increasingly faint. There will be no more galaxies, no more stars, and no more systems capable of sustaining life. The universe, once vibrant with activity, will enter its final stage of silence. This state will stretch across unimaginable timescales, billions and trillions of years, during which the universe slowly fades into an eternal stillness. The heat death represents the final outcome of the universe's expansion and the inevitable consequence of the increasing entropy that accompanies it. However, this does not mark the end of all possibilities. The fabric of space-time itself may continue to evolve, and the quantum fluctuations that exist even in a vacuum may lead to unexpected events. Though these fluctuations are incredibly small, they are an essential feature of quantum theory. Over vast timescales, there may be moments of activity or change, but they would not be the kind of processes that could sustain complex systems or life. Instead, the universe will gradually shift toward a state of maximum disorder and inactivity. This period of stillness, sometimes referred to as the long sleep of the universe, represents the final chapter in the cosmic journey. It is a universe in which nothing changes, nothing evolves, and nothing exists except for the faint traces of what once was. While the fate of the universe is set in motion by the expansion and the increasing entropy, it is important to note that the universe will not reach this final state immediately. The timeline is immense, stretching over billions and trillions of years. The last active stars will die, leaving behind remnants like black holes and white dwarfs. As the galaxies continue to move apart, the fabric of the cosmos will thin out. New stars will form less frequently, and eventually star formation will cease altogether. In the distant future, even black holes, the most mysterious and powerful objects in the universe, will evaporate over time, their mass slowly radiated away, until they too disappear. Once the last stars have burned out and the black holes have evaporated, the universe will have reached a state of absolute cold and darkness. In this final stage, all that will remain are the simplest particles, protons, electrons, and the remnants of what were once the building blocks of stars and galaxies. The universe will have reached the end of its story, not with an abrupt conclusion, but with a slow, inevitable fade into emptiness. The passage of time will become irrelevant, as nothing will remain to mark its passage. The universe will be a silent, dark expanse forever frozen in a state of stillness and entropy. While the final moments of the universe are far beyond our lifetime, the knowledge of its eventual end shapes our understanding of its origins and its evolution. The expansion of the universe, the formation and death of stars, the role of dark energy and the inevitability of entropy combine to create a picture of a cosmos that is at once both incredibly dynamic and ultimately bound for stillness. As we look to the stars and the galaxies, we are reminded that even the greatest forces of nature, the ones that have shaped the universe for billions of years, are subject to the passage of time, and that time in the end will leave its mark on the universe itself. The universe's ongoing expansion and the presence of dark energy lead to one of the most fundamental questions about the future of the cosmos. Will the universe continue to expand forever? And if so, what will be the ultimate consequences of this unending expansion? As the galaxies, stars, and other cosmic structures move farther apart, the universe will grow increasingly isolated. This isolation will be driven by the force of dark energy, which causes the acceleration of the universe's expansion. The discovery of dark energy in the late 20th century changed our understanding of the cosmos, revealing that the expansion, which was initially expected to slow due to the influence of gravity, is instead speeding up. This acceleration will continue indefinitely, pushing galaxies further from one another at an ever-increasing rate. Over vast timescales, the galaxies we observe today will no longer be visible to each other. They will be so far apart that no light will travel between them, and their individual fates will be sealed by their isolation in an ever-expanding void. The eventual consequence of this accelerated expansion is a scenario in which the universe becomes cold, dark, and empty. Stars will burn through their fuel and die, leaving behind remnants like white dwarfs, neutron stars, and black holes. As galaxies drift apart, the gas and dust that were once the building blocks for new stars will become increasingly diffuse, making the formation of new stars increasingly unlikely. Over time, the remaining stars will grow older and burn out, leaving behind only faint traces of their past activity. The universe will be a place of darkness, devoid of the light that once illuminated it. No new stars will form, and the remnants of old stars and galaxies will be scattered across the vast expanse of space, isolated and disconnected. The fabric of space itself will continue to stretch, and as the distance between galaxies increases, the energy that once fueled the universe's growth will be stretched thinner and thinner. Eventually, the energy that once powered the cosmos will dissipate, leaving a cold, empty expanse that no longer supports the processes of star formation, galaxy collision, or the birth of new structures. As this expansion continues, the fate of individual galaxies becomes increasingly uncertain. Some galaxies may eventually become gravitationally unbound with their stars and remnants spread across the cosmos. Others may collide and merge into larger galaxies, though this process will become less common as the universe continues to expand. Even when galaxies do collide, the rate of star formation will slow, and the resulting new stars will be fewer and fewer. Over time, galaxies will evolve into isolated systems, each drifting through the cold expanse of space, unable to interact with one another. The intergalactic medium, the gas that fills the space between galaxies, will become increasingly sparse, and as it thins, the process of galaxy formation will cease. In this way, the expansion of the universe will not just lead to the isolation of galaxies, but also the end of the processes that created them in the first place. The final stages of the universe's expansion will see the death of the last stars. These stars, which burn hydrogen and helium in nuclear fusion reactions, will eventually exhaust their fuel and begin to cool and fade. Smaller stars will become white dwarfs, their cores remaining intact as they slowly cool over billions of years. Larger stars will become neutron stars or black holes, their remains more compact and dense than anything else in the universe. While black holes can continue to grow by accreting matter from their surroundings, they will eventually lose mass through a process called Hawking radiation. This process, theorized by Stephen Hawking in the 1970s, causes black holes to emit radiation and gradually lose mass over time. As the black hole evaporates, it will shrink until it disappears completely, leaving nothing behind but radiation. This gradual evaporation of black holes, combined with the death of the last stars, will leave the universe without any active sources of light or energy. As the universe becomes increasingly empty, the remnants of its once vibrant activity will slowly fade into oblivion. the process of star formation will cease, and the galaxies, stars, and black holes that remain will eventually become cold and dark. This state, known as the heat death of the universe, will be characterized by an almost perfect state of entropy, where energy is evenly spread out and no thermodynamic processes can occur. The universe will be a place of absolute stillness, with no stars shining, no galaxies colliding, and no energy available for meaningful work. This process will take billions to trillions of years, but in the end it will lead to a universe devoid of life activity and change. The once bustling universe full of stars, galaxies, and cosmic events will become a silent and empty expanse. Though this scenario may seem bleak, it is important to recognize that the heat death of the universe is only one possible outcome, and it is a long way off. The eventual end of the universe is not a sudden event, but rather a gradual process that will unfold over an incredibly long period. The universe's future will be shaped by the continuing expansion of space, the death of stars, and the eventual dissipation of energy. While the universe will eventually reach a state of maximum entropy, this will not occur until the last stars burn out and the last remnants of matter are spread thin across the cosmos. Even after that, there may still be some trace of the universe's past activity preserved in the faint radiation that remains. The heat death of the universe is a reminder of the transitory nature of all things. The processes that govern the formation and death of stars, galaxies, and black holes are part of a larger cosmic cycle, one that will eventually come to an end. The universe as we understand it will eventually fade into darkness, leaving behind only the remnants of its once vibrant existence. But even as the universe moves toward this inevitable end, its story is far from over. The fate of the universe will unfold over billions of years, and in that time many more stars will be born, many more galaxies will collide, and many more black holes will form. The universe's final end may still be a long way off, but the forces that govern its evolution, dark energy, gravity, and entropy, continue to shape its future. As the universe continues its expansion, driven by the mysterious force of dark energy, the structure of the cosmos gradually shifts toward isolation and emptiness. The accelerated expansion not only drives galaxies further apart, but also contributes to the gradual dissolution of the cosmic web, the interconnected structure formed by galaxies clusters and superclusters of galaxies. Over time, as the space between galaxies stretches, the gravitational pull that once held clusters of galaxies together becomes less effective. Galaxies will drift further from each other with no new forces acting to bring them back together. This isolation will lead to a situation where the cosmic structures we observe today, the intricate clusters and superclusters of galaxies, are spread thin, leaving the universe largely devoid of the dense gravitationally bound systems that are common today. Galaxies once closely linked in groups will become isolated islands of stars scattered across an ever-expanding void. As this expansion continues, the consequences for the formation of new stars become increasingly apparent. The intergalactic medium composed of gas and dust will become more diffuse as the universe grows. The remaining gas, which is necessary for star formation, will become increasingly sparse, making it harder for new stars to form. Star formation, which has occurred in galaxies since their inception, will slowly grind to a halt. While some new stars may still form in the distant future, they will be far fewer in number and much more isolated as galaxies become increasingly distant from one another. The death of stars, whether through supernovae, the collapse into white dwarfs, or the formation of black holes, will eventually leave behind remnants that no longer have the potential to create new stars. The cooling of the universe will make it increasingly inhospitable to the active processes that create and sustain stars, leading to a universe that grows quieter and dimmer. As stars die and the supply of gas dwindles, the fate of individual stars becomes more apparent. Massive stars, having exhausted their nuclear fuel, will explode in supernovae, releasing vast amounts of energy and spreading elements like carbon, oxygen, and iron throughout the universe. These elements forged in the cores of stars are the building blocks for planets, and in some cases life. But after these supernovae, the universe will be left with the remnants of the stars, the cores that become neutron stars, black holes, or white dwarfs. Neutron stars, incredibly dense remnants of massive stars, will remain for billions of years, though they too will eventually cool and fade into darkness. Black holes, the most massive remnants of dying stars, will continue to exert their powerful gravitational pull on the surrounding space. These black holes will gradually grow as they accrete more matter, but over the course of trillions of years, even they will fade away through the process of Hawking radiation, a phenomenon that causes black holes to slowly lose mass and energy. The eventual evaporation of black holes marks one of the last stages of cosmic evolution. Though black holes are some of the most mysterious and powerful objects in the universe, their fate is ultimately tied to the same forces that govern the rest of the cosmos: entropy, gravity, and time. As they lose mass through Hawking radiation, black holes will eventually shrink, becoming smaller and more concentrated until they vanish entirely. This process of evaporation, though incredibly slow, will take place over incredibly long timescales, far longer than the current age of the universe. The end of the last black hole represents a major milestone in the death of the universe, as it marks the final stage of the most massive objects in the cosmos. Once the last black holes have evaporated, all that will remain will be the faint remnants of radiation scattered across an ever-expanding void. But even after the last stars have died and the last black holes have evaporated, the universe may still contain some remnants of its past. These remnants may consist of subatomic particles, remnants of dark matter, or traces of radiation from the early universe. While these remnants will be faint and scattered across vast distances, they will represent the last vestiges of the once vibrant cosmos. The universe, now empty and dark, will be a cold and lifeless place. The death of stars, the evaporation of black holes, and the eventual dissipation of matter will leave behind a universe devoid of activity or change. The only remaining source of energy will be the faint radiation that lingers from the early moments of the universe's existence, radiation that has been stretched and diluted by the ongoing expansion. As the universe approaches this final state, it will become increasingly difficult for any processes of meaningful change to occur. The vast distances between galaxies and the lack of available energy will prevent new structures from forming. The universe will exist in a state of maximum entropy where everything is spread as thinly as possible, and no more useful energy can be extracted. This state of absolute entropy is known as the heat death of the universe, and it represents the final, inevitable fate of the cosmos. Over time, as all matter becomes more and more dispersed, the universe will reach a state of stillness where no significant events or processes take place. There will be no stars, no galaxies, and no life. The universe will be a place of cold, dark silence, where nothing moves, changes, or evolves. This eventual fate of the universe is a direct consequence of the laws of thermodynamics. The second law of thermodynamics states that the total entropy of an isolated system can never decrease. As the universe expands and energy is spread more evenly, the total entropy of the universe increases, leading to a state where no useful energy remains. The process of entropy is irreversible, meaning that once the universe reaches a state of maximum entropy, there will be no turning back. The heat death of the universe represents the ultimate endpoint of this process, a state where the universe will have exhausted all its available energy and ceased all meaningful activity. The expansion of the universe and the death of stars, galaxies, and black holes represent a long and gradual process that will take billions to trillions of years to unfold. The universe will continue to expand, galaxies will continue to drift apart, and the remnants of stars will continue to cool and fade away. But in the end, the universe will reach a point where no more significant changes can occur, and the forces that once shaped its evolution will have run their course. The universe will be left in a state of absolute stillness and entropy, a cold and dark remnant of the once vibrant cosmos. Though this end is distant, it is a natural consequence of the forces that have governed the universe since the Big Bang. As the universe moves towards its inevitable end, the gradual unfolding of its final moments will be shaped by forces already in motion. The expansion driven by dark energy continues to stretch the fabric of space-time, pushing galaxies further apart, isolating them in an ever-widening void. This continuing expansion leads the universe toward a future of increasing emptiness. Over time, galaxies once part of large connected cosmic structures will become isolated islands, each one drifting farther from its neighbours. In a distant future, galaxies will no longer be able to interact gravitationally, and the intricate web of galactic clusters and superclusters will dissolve. The cosmos will become increasingly fragmented as the space between its components grows larger and larger. This growing isolation will have profound effects on the fate of stars and the material that once formed galaxies. The intergalactic medium, the gas and dust that fill the space between galaxies, will become increasingly diffuse, its ability to form new stars diminishing as the universe ages. The process of star formation, which has continued for billions of years, will slowly grind to a halt. The gas necessary for star creation will be spread thinner and thinner across the vast emptiness, making it less likely that new stars will form. In the distant future, the universe will be a place where stars no longer ignite in the same way, and the vibrant, active cosmos we know today will give way to a still dark and cold universe. The stars that remain, once burning brightly, will eventually exhaust their nuclear fuel. For stars like the Sun, this process involves expanding into a red giant before shedding their outer layers and leaving behind a dense white dwarf. For more massive stars, the fate is even more dramatic. These stars end their lives in violent supernova explosions, scattering heavy elements into space. The remnants of these supernovae either form neutron stars, incredibly dense objects, where gravity has crushed the matter into a small space, or black holes regions where gravity is so strong that not even light can escape. These black holes, which can grow over time by accreting matter from their surroundings, represent some of the most mysterious and powerful objects in the universe. However, even black holes are subject to the passage of time. Over extremely long periods, the phenomenon known as Hawking radiation will cause black holes to lose mass and energy. This radiation, theorized by Stephen Hawking, results from quantum effects near the event horizon of black holes. Eventually, the black holes will evaporate, disappearing entirely into the vast void of space. Though the timescales for this process are unimaginably long, trillions of years, the eventual evaporation of black holes will mark the end of the most massive objects in the universe, leaving behind only faint traces of their existence. As the last stars burn out and the last black holes evaporate, the universe will be left in a state of near-perfect entropy. The energy that once fueled the formation of stars, galaxies, and the complex structures of the cosmos will have dissipated. The universe, which began as a hot and dense point, will have cooled and stretched to the point where no more significant processes take place. This stage of universal decline is known as the heat death of the universe. It is a state where all matter is evenly distributed, with no usable energy left to drive physical processes. The remnants of the stars, the white dwarfs, neutron stars, and black holes will be the last objects in the universe, and even they will eventually fade away. The heat death represents the ultimate end of the universe's dynamic processes, the final outcome of its ongoing expansion, and the relentless increase of entropy. Though the heat death of the universe is one possible outcome, other scenarios have been proposed by physicists, including the Big Crunch and the Big Rip. The Big Crunch suggests that the expansion of the universe could eventually slow down and reverse, causing the universe to collapse back on itself. In this model, gravity would overcome dark energy, pulling galaxies, stars, and all matter together in a catastrophic collapse. However, current observations suggest that the universe's expansion is accelerating, making the Big Crunch less likely. The Big Rip, another possible outcome, proposes that the universe's expansion will continue to accelerate, eventually tearing apart galaxies, stars, planets, and even atoms. This scenario would be driven by dark energy, which would overcome all gravitational forces, leading to the disintegration of everything in the cosmos. While the Big Rip remains a theoretical possibility, it is unclear whether this scenario will play out. Despite the uncertainties about the exact fate of the universe, the heat death remains the most widely accepted outcome. It is a future defined by a gradual decline into a state of maximum entropy, where all matter is evenly distributed and no significant change can occur. As the universe approaches this final state, all activity will cease. The last sources of energy, stars, black holes, and other remnants, will have disappeared, and the cosmos will be left in a dark, cold, and empty state. The process of expansion and entropy will have reached its peak, and there will be no more stars, galaxies, or even black holes to provide any form of structure or activity. The universe will be silent with nothing left to disturb the stillness. This eventual end of the universe is a direct consequence of the laws of thermodynamics, particularly the second law, which states that the total entropy of a closed system can never decrease. As the universe continues to expand, the available energy becomes more evenly spread out, leading to a state of higher entropy. Over time, all the processes that require energy, such as star formation, galaxy collisions, and the movement of matter will come to an end. The universe will reach a point where all its energy is evenly distributed, and no new events or activities will take place. It will be a place of stillness where nothing changes, nothing moves, and no processes occur. This state of perfect entropy marks the end of the cosmic cycle, the final chapter in the universe's story. The end of the universe is still billions to trillions of years away, and the processes that will lead to its demise are already underway. The stars that burn brightly today will eventually fade into darkness, and the galaxies that are currently interacting with one another will drift apart, unable to influence each other due to the expansion of space. The death of stars and the evaporation of black holes will mark the gradual decline of the universe into a state of stillness. The final moments of the universe will be cold, dark, and empty, with no stars to light the way. As entropy increases and all activity ceases, the universe will become a place where time itself loses its meaning. It will be a universe that no longer changes, a universe that has reached the end of its journey. As the universe continues its gradual march toward the heat death, the last remnants of activity fade into the dark expanse of space. Stars have burned out, black holes have evaporated, and the remaining matter has been scattered so thinly across the cosmos that it no longer forms coherent structures. The universe, once a dynamic and vibrant place, will become a cold, dark, and empty void. With no remaining sources of energy or light, the universe will be devoid of the processes that once sustained it. There will be no more stars forming, no more galaxies colliding, and no more life. The expansion of the universe continues unabated, but the forces that once shaped it are gradually losing their influence. Gravity, which once brought galaxies together and formed stars, becomes irrelevant over long distances as space stretches. With no significant sources of light or heat, the universe becomes increasingly inhospitable, with the remaining energy becoming more evenly distributed. In this state of maximum entropy, there will be no movement, no change, and no activity. Time as we understand it will lose its meaning in a universe where no events unfold and no new phenomena emerge. Over the course of trillions of years, even the faint radiation that lingers from the early universe will fade away, stretched thin by the continued expansion. This radiation, the cosmic microwave background, once provided a window into the earliest moments of the universe's life, but as the universe expands, its energy becomes more diluted. The cooling of the universe, driven by the expansion and the steady dissipation of energy, will result in a state where no significant thermal processes occur. There will be no more stars to emit light, no more galaxies to interact with each other, and no more black holes to devour matter. The universe will be a place where the laws of physics still apply, but they will no longer lead to any meaningful change. At this stage, the universe will have reached the final phase of its evolution, a state of absolute calm where all matter and energy are distributed so evenly that no significant processes are possible. The once vibrant cosmos, full of galaxies, stars, and dynamic events, will be reduced to an almost empty void, with only the faintest traces of its past activity remaining. The death of stars and the eventual evaporation of black holes will leave behind only the simplest particles, Protons, electrons, and neutrinos all scattered across the cosmos in an ever-expanding void. These particles will continue to drift, but the lack of gravitational or other forces to bind them together means that they will never form new structures. The universe will continue to expand, but there will be no new formation of stars, planets, or galaxies. The process of entropy that has been ongoing since the Big Bang will have reached its peak. Entropy, which measures the degree of disorder in a system, will have increased to the point where all energy is evenly distributed throughout the universe. No energy will be available to drive processes such as star formation or the movement of galaxies. The universe will have exhausted all its available energy, and no new events will occur. The state of maximum entropy is one in which no work can be done, and no significant change can take place. The universe will be a place where time itself seems to slow, and the processes that we associate with the passage of time, change movement and activity, cease entirely. While the universe may continue to expand indefinitely, it will eventually reach a state where no processes can occur and no new structures can form. This state is sometimes referred to as the heat death of the universe, a time when the universe has reached its ultimate state of stillness. The universe will be cold and dark with no stars to light the way. It will be a place where the passage of time is irrelevant, as nothing will change. This final phase of the universe's life, though still far in the future, represents the inevitable end of its long, complex journey. It is the natural consequence of the expansion and the increasing entropy of the cosmos. As the universe approaches this final state, it is clear that the forces that have shaped it, gravity, dark energy, and the fundamental interactions between particles, have all played their part in bringing about this end. Gravity, which once brought galaxies together and formed stars, becomes insignificant as galaxies drift farther apart. Dark energy, which drives the accelerated expansion of the universe, continues to stretch space, but it will no longer be able to create new structures or support life. The fundamental interactions between particles will continue, but they will no longer lead to meaningful change. The universe, once full of activity, will become a place of complete stillness, with nothing left to create or destroy. This final state of the universe will not be the end of time itself, but rather the end of all processes that make time meaningful. In the distant future, time will continue to pass, but it will no longer be associated with any change. The universe will have entered a state of stasis where no new events unfold and no new structures emerge. It will be a universe where the passage of time is no longer measurable by the processes that once defined it. Time as we understand it will have lost its significance in a universe where entropy has reached its peak and no further change is possible. The heat death of the universe represents the final chapter in the cosmic story. It is the ultimate fate of a universe that has expanded, cooled, and evolved over billions of years. The universe, once full of stars, galaxies, and life, will become a cold, dark, and lifeless place. The forces that once shaped it will have run their course, and the universe will be left in a state of complete stillness. The final moments of the universe, though unimaginably distant, are already set in motion. The stars will die, the galaxies will drift apart, and the energy that once powered the cosmos will dissipate, leaving behind only the faintest traces of a once vibrant universe. While this ultimate fate may seem inevitable, it is a reminder that all things have a beginning and an end. The universe, like all systems, is subject to the laws of physics and the forces that govern its evolution. The heat death represents the culmination of the universe's long journey, but it also marks the natural conclusion of the processes that have driven its evolution since the Big Bang. As the universe fades into darkness, its story will have come to an end, and the cosmos will be left in a state of perfect entropy, a silent testament to the passage of time and the inevitable fate of all things. In the distant future, as the universe continues its expansion, even the most stable remnants of the cosmos will eventually succumb to the relentless forces at work. The death of stars, the evaporation of black holes, and the gradual decay of matter will leave the universe in a state of profound silence and stillness. While the universe may continue to expand indefinitely, This expansion will only increase the isolation between its remnants. No longer will galaxies collide or interact with each other as the force of dark energy stretches space at an accelerating rate. The visible universe we know today, filled with vibrant stars, planets and galaxies, will become increasingly sparse and distant. Over time, the once dominant gravitational interactions that form the building blocks of galaxies and solar systems will become weaker, and the connections between objects in space will fade. The process of gravitational collapse, which once brought galaxies and stars together, will no longer be effective as objects become more and more isolated. As this isolation grows, the physical processes that once fueled the formation of stars and galaxies will come to an end. Star formation, a process that has created new generations of stars for billions of years, will cease. The raw material for new stars, the gas and dust that exist in the space between galaxies, will become more and more dispersed across the ever-expanding universe. The energy necessary for these processes to continue will be spread thinner and thinner until it no longer exists in sufficient quantities to form new stars. The remaining gas and dust in the universe will be too diffuse to condense into the dense clouds necessary for star formation. The rate of star birth will slow, and eventually the last stars will burn out, leaving behind only the remnants of their once bright existence. White dwarfs, neutron stars, and black holes will be the last objects to shine in the universe, but even these will eventually fade away. The death of stars and the cessation of star formation will mark the end of one of the most fundamental processes that shape the universe. Stars not only provide light and energy, but they also create the elements necessary for the formation of planets' life and the structures we observe today. The death of stars through supernovae or the gradual cooling of white dwarfs will leave behind the heavier elements they produced, but without new stars to give birth to new life, these elements will be scattered across the universe, unable to form into new systems. The energy needed to drive these processes will become increasingly scarce as the universe expands and cools, and the process of star formation will grind to a halt. The black holes that remain after the deaths of massive stars will continue to exist for much longer, but even they are not immune to the passage of time. Black holes once formed grow by pulling in matter from their surroundings, accumulating mass and energy. Over time, however, they lose mass through Hawking radiation, a process predicted by physicist Stephen Hawking in 1974. This radiation emitted from the event horizon of black holes causes them to lose mass gradually, and over an inconceivably long period, black holes may eventually evaporate completely. The timescales for this process are staggering, with the largest black holes potentially taking trillions of years to evaporate. However, even the black holes that once ruled over galaxies, shaping the movements of stars and gas, will eventually fade into nothingness, leaving behind no trace of their once powerful presence. As the last stars burn out and black holes evaporate, the universe will become increasingly dark and cold. The remnants of once vibrant galaxies will be spread thin across an ever-expanding void. The interactions between galaxies once common and violent will cease as the distance between them grows larger. The galaxies themselves will eventually stop forming new stars, leaving behind only the old remnants of their past lives, white dwarfs, neutron stars, and the faded traces of their earlier existence. The energy required to fuel life star formation, and any kind of significant activity, will be depleted, and the universe will reach a point where nothing of substance remains. The slow cooling of the universe will continue as it stretches toward a state of maximum entropy, where all matter is spread so thinly that no more processes can take place. The end of the universe will not come in a sudden dramatic burst, but in a gradual, inexorable decline into cold, dark stillness. As the last stars die and the black holes evaporate, the universe will become increasingly isolated and empty. The last particles of matter will drift through the vast emptiness, disconnected from one another by the immense distances of expanding space. The once dynamic cosmos, full of stars, galaxies, and activity, will have come to a quiet end, and the passage of time will become irrelevant in a universe where nothing changes. time as we experience it will lose its meaning as the universe's processes slow to a halt. The universe will no longer be a place of motion or transformation, but will instead exist as a static, lifeless remnant of its former self. The heat death of the universe, in which all available energy is used up, and the cosmos reaches a state of maximum entropy, represents the ultimate outcome of the universe's expansion. It is the logical conclusion of the forces that have shaped the universe since the Big Bang, and it marks the end of all processes that rely on energy. In this final state, the universe will be a place where no stars shine, no galaxies collide, and no significant changes take place. The universe will be a cold, dark, and empty expanse with no energy left to power any form of life or activity. The silence of this final state will be absolute, with no events to disturb the stillness. As the universe reaches this state, it will have fulfilled its cosmic cycle. The forces of gravity, dark energy, and entropy will have run their course, and the universe will be left in a state of perfect equilibrium, where no further change is possible. While this final end is still billions of years away, the path to it has already been set into motion. The expansion of space, the cooling of stars, and the eventual decay of black holes will bring the universe to its ultimate conclusion, a universe of quiet, cold, and dark emptiness. The forces that once shaped the cosmos into a vibrant, active place will have faded, and the universe will enter its final phase of stillness, marking the end of everything. As the universe continues to expand, its fate becomes more apparent, marked by the gradual dissipation of all the forces that once shaped its structure and dynamics. The cooling of stars, the isolation of galaxies, and the eventual evaporation of black holes all signal the irreversible decline of the cosmos. The universe, once a lively and complex place full of stars, galaxies, and dynamic processes, will slowly fade into a state of inactivity. The transition from the active, ever-changing cosmos we observe today to a cold, dark, and empty universe is not abrupt, but a slow, inevitable process driven by the underlying forces of expansion, gravity, and entropy. One of the primary consequences of this expansion is the gradual depletion of the resources needed to fuel the processes of star formation. The gas and dust that fuel the birth of new stars, which once filled the space between galaxies, will become more and more dispersed across the ever-expanding universe. As this gas thins out, star formation will become increasingly rare. The remaining stars will burn through their fuel, and over time the number of stars still shining in the universe will dwindle. The death of stars will lead to the formation of dense remnants, like white dwarfs, neutron stars, and black holes. These objects, while still significant in their own right, will not be able to sustain the same processes that form the stars, and the universe will be left with only the remnants of its once vibrant activity. Black holes, some of the most mysterious and powerful objects in the universe, will continue to play a central role in its final moments. While black holes can grow by accreting matter from their surroundings, their influence will gradually decrease over time. The process of Hawking radiation, a quantum phenomenon that causes black holes to lose mass, will eventually cause these massive objects to shrink and evaporate. This process, though incredibly slow, will result in the eventual disappearance of black holes, leaving behind nothing but the faintest traces of their former existence. The evaporation of black holes, which will take place over timescales much longer than the age of the universe, is a critical aspect of the universe's ultimate fate. As they fade, black holes will leave behind no visible remnants, signaling the final departure of the most massive objects in the cosmos. Once the last stars have died and the last black holes have evaporated, the universe will become an almost completely empty space. The energy that once powered the universe's evolution will have been used up, and the forces that once shaped galaxies, stars, and planets will no longer be effective. The cooling process will continue with the temperature of the universe slowly approaching absolute zero. In this state of near-perfect entropy, no new events or processes will take place. The universe will be a place of total stillness where no matter or energy can perform any work. The once active cosmos will have become a cold, dark, and lifeless expanse with no hope for new stars, planets, or life. However, even in this final state of universal decline, some traces of the past will remain. The faintest particles, possibly remnants of dark matter or radiation from the early universe, will continue to exist, though they will be spread so thin across the cosmos that they will have little to no impact on the universe's behaviour. Over the course of trillions of years, even these particles will become increasingly sparse, and the universe will enter a phase where nothing significant occurs. Time itself, though it will continue to pass, will lose its meaning in a universe where no processes unfold, no matter changes, and no energy remains to sustain life or activity. The universe will be locked in an eternal state of stasis, and the passage of time will be irrelevant as there will be no events to measure it against. The process of entropy that drives the universe toward this final state is a slow, inevitable one. As the universe continues to expand, its energy becomes more evenly spread out, and the processes that once gave it structure and meaning, such as star formation, galaxy collisions, and the birth of new matter, come to an end. The universe's future is governed by the forces that have shaped it. Since its inception, the expansion of space driven by dark energy, the gravitational pull that once brought galaxies and stars together, and the gradual increase in entropy that leads to the eventual decay of all matter. The heat death represents the ultimate end of this process, where no more meaningful activity can occur. The universe, once a place of dynamic change and creation, will become a place of stillness and silence. As time stretches on, the universe will become increasingly desolate. The stars that once lit up the sky will have burned out, and the remnants of their once great power will be scattered across an ever-widening void. Galaxies will drift further apart, isolated from one another by the accelerating expansion of space. The fabric of space itself will stretch so thin that it will become impossible for new structures to form. The matter that once composed stars, planets, and galaxies will be so dispersed that it will no longer be able to interact in any meaningful way. The once glorious light of stars will be replaced by the cold, dim remnants of their existence, white dwarfs, black holes, and the last traces of the matter that once made up the universe's vibrant structures. This final state of the universe, where no processes take place and no changes occur, is the ultimate consequence of the expansion and entropy that have been at work since the Big Bang. While this end may seem distant, it is already set into motion. The universe, like all things, will eventually come to an end. But this end is not a violent one. It will not be marked by sudden destruction, but by a slow and inevitable fade into stillness. The universe will stretch, grow cold, and become empty, and in the end there will be no more stars to light the way, no more galaxies to bring structure to the cosmos, and no more life to witness the passage of time. The universe will have completed its long, slow journey, from its fiery beginning to its silent, cold end, and in that end time will lose its significance. As the universe's expansion accelerates, and the forces of gravity become increasingly irrelevant, the ultimate fate of all remaining cosmic structures becomes more apparent. Galaxies once grouped into clusters and superclusters will continue to move further apart, leaving them isolated in an ever-expanding universe. The gravitational forces that once bound these structures together will no longer be able to hold them, and over time the cosmic web of galaxies will begin to unravel. The interactions that have shaped the universe for billions of years will cease, and the once rich environments of galaxies will be stripped of their active processes. The stars within these galaxies, once vibrant and full of life, will continue their slow decline. Even the most massive stars, which once burned brightly at the centres of galaxies, will eventually exhaust their fuel. The process of stellar death, from the explosion of supernovae to the formation of white dwarfs, neutron stars, and black holes, will leave behind only the remnants of these once powerful objects. Over unimaginable timescales, even these remnants will fade as their energy is gradually dissipated into the cold expanse of space. In the absence of new stars, and with the gradual decline of the remnants of old ones, the universe will become increasingly dark and cold. The The last stars will have burned out, leaving behind only faint embers in the form of white dwarfs and neutron stars. These stellar remnants, which once held the promise of continued activity and cosmic creation, will eventually cease to exist as their energy fades. White dwarfs will slowly cool, unable to sustain any processes that could regenerate energy. Neutron stars too will eventually lose their remaining energy, and the black holes that form from collapsing stars will continue to grow, albeit at a slower pace as they accrete matter. However, black holes too are not immune to the passage of time. Over the course of trillions of years, black holes will gradually lose mass through Hawking radiation, a process that will eventually cause them to evaporate. The timescale for this evaporation is so long that it exceeds the current age of the universe by many orders of magnitude, but it is an inevitable process that leads to the gradual disappearance of even the most massive objects in the cosmos. Once the last black holes have evaporated, the universe will be a place where matter no longer exists in any meaningful form. The energy that once powered stars, galaxies, and even black holes will have been used up or dissipated, and the remnants of the cosmos will be left in a state of perfect entropy. The universe will have reached its final static phase 1, where no new stars will form, no new structures will emerge, and no significant changes will occur. The expansion of space will continue, but it will no longer be able to drive the processes of creation or evolution. The once vibrant universe will have become a cold, dark, and empty place, where all activity has ceased. The final remnants of energy, like the last photons of light from dead stars, will fade into the vast emptiness, leaving the universe in a state of permanent stasis. The temperature of the universe, once defined by the heat of stars and galaxies, will continue to decrease as the universe expands. Eventually it will approach absolute zero, the temperature at which no more thermal energy remains. This marks the point at which the universe reaches its maximum state of entropy, where no processes can occur and all matter exists in its most disordered form. At this temperature, no chemical reactions can take place, and no energy can be harnessed to drive any meaningful processes. All matter will be frozen in time with no more changes or transformations occurring. The universe, once filled with motion, will become a place where time and change lose their meaning. The end of the universe in this state of perfect entropy is sometimes referred to as the heat death of the universe. This term captures the idea that the universe, having reached the point of maximum disorder, will no longer be able to sustain any activity. It will be a universe where the forces that once governed its behaviour, gravity, electromagnetism, and nuclear interactions, will no longer have any effect. There will be no more stars, no more galaxies, no more life, and no more motion. The universe will be reduced to a static, featureless expanse, a dark, cold, and silent void where nothing ever changes. This state represents the ultimate fate of the universe, a gradual and inevitable process that will unfold over billions, then trillions of years as the cosmos moves toward its final end. While the heat death of the universe is the most widely accepted model for the end of the cosmos, it is important to recognize that this scenario is not the only possible outcome. Alternative theories such as the Big Rip and the Big Crunch present different possibilities for the universe's end. In the Big Rip scenario, the universe's expansion would continue to accelerate indefinitely, tearing galaxies, stars, and even atoms apart. In the Big Crunch, the universe's expansion would slow down and eventually reverse, causing everything to collapse back into a singularity. These alternative scenarios, while intriguing, are less favoured by current observations, which point to the accelerating expansion of the universe due to dark energy. Nevertheless, the heat death remains the most widely accepted model based on our current understanding of cosmology. The fate of the universe, whether it leads to heat death, a big rip, or a big crunch, is a reminder of the transient nature of all things. Just as stars are born, burn out, and eventually die, so too will the universe. The processes that shape the cosmos, from the formation of stars to the death of black holes, are part of a larger cosmic cycle that ultimately ends in a state of stillness and silence. The universe, once full of activity and creation, will gradually fade into darkness. The passage of time as we understand it will lose its relevance as the universe reaches a point where no further events occur and no new structures form. Despite the inevitability of this end, the journey of the universe from its fiery birth to its eventual decay is a story that spans trillions of years. It is a story of creation, evolution, and destruction, where the forces of gravity, dark energy, and entropy have shaped the cosmos into what we observe today. The universe, though it will eventually come to an end, has been through countless transformations, and its history remains etched in the stars, galaxies, and cosmic remnants that continue to exist. And even in its final moments, the universe will bear witness to the passage of time, reminding us of the impermanence of all things. As the universe's end looms ever closer, the cosmic forces that shaped it will have long faded into irrelevance. The gradual spread of matter and energy, the cooling of stars, and the relentless expansion of space will all have reached their final stages. The universe, once a vibrant expanse of energy, matter, and activity, will have transformed into a vast, empty, dark void, where the passage of time loses its meaning. The final moments of the universe will unfold across incomprehensible timescales, with nothing to interrupt the inevitable quiet that will engulf it. No stars will burn, no galaxies will collide, and no new structures will emerge. The once dominant forces, gravity, electromagnetism, and the nuclear interactions will have no role left to play in the cold, featureless void that the universe will become. The fate of everything in the cosmos, from the largest galaxies to the smallest particles, will be tied to this final, irreversible process of decay and dissolution. At the heart of this cosmic decline lies the increasing entropy of the universe. Entropy, which measures the amount of disorder in a system, has been growing steadily since the Big Bang. As the universe expands, the energy within it is spread more thinly, and the once ordered structures of stars, galaxies, and clusters are replaced by increasingly disordered remnants. The second law of thermodynamics tells us that entropy always increases in a closed system, and as the universe approaches maximum entropy, no further work can be done. This marks the ultimate conclusion of the universe's long history, where everything has reached a state of equilibrium and no change or meaningful interaction is possible. The stars and galaxies, once the building blocks of a dynamic and evolving cosmos, will have burned out and faded, leaving nothing but the faintest traces of their former existence. Over time, even these traces will dissipate, leaving behind a universe that is silent, dark, and devoid of any motion or activity. The expansion of the universe will continue, but at a vastly diminished rate. As galaxies move farther apart, the forces that once drew them together, gravity, will become ineffective over increasingly larger distances. Eventually, the remaining structures in the universe, whether white dwarfs, neutron stars, or the faint remnants of dead galaxies, will be so scattered across the vastness of space that they will no longer be able to interact. With no fuel to sustain star formation and no means for gravity to bring matter together, the universe will descend into a state of cosmic stasis. The once dominant process of stellar evolution, birth, life, and death will be a distant memory as stars, the engines of creation in the cosmos, will no longer shine. With no new stars or galaxies forming, the universe will enter a phase of gradual quiet decline, marked only by the slow, inevitable cooling of what remains. The end of the universe is not a violent cataclysmic event, but rather a slow fade into nothingness. The stars, once the source of light and heat, will exhaust their fuel and die, leaving behind cold remnants like white dwarfs and neutron stars. Black holes, which will have consumed much of the remaining matter, will continue to exist for a time, but they too will slowly evaporate through Hawking radiation. As the last black holes evaporate, and the last remnants of stars cool and fade, the universe will be left with only the faintest traces of its past activity, particles of matter scattered across an ever-expanding void. These particles will drift in isolation, unable to form any new structures. The universe will no longer have the energy or the matter to create new stars or galaxies. The cosmic expansion, though still ongoing, will stretch the very fabric of space itself, causing everything to be increasingly isolated from one another. The distance between galaxies will grow so large that no interactions will remain, and the universe will be a place where change and motion are no longer possible. As the universe's remaining energy is slowly dissipated, the temperature will drop, approaching absolute zero, the point at which all thermal motion ceases. This marks the final moment in the cosmic timeline when the last vestiges of heat and energy are gone. The laws of physics which once governed the behavior of stars and galaxies will no longer be able to drive any processes. There will be no more light, no more stars, and no more life. The universe, once full of potential, will have reached a state of perfect entropy, where all particles are evenly distributed and no usable energy remains. In this final state, time will have no meaning as there will be no events to mark its passage. The universe will simply exist as a silent, featureless void, its past activity reduced to nothing but the faintest trace. The heat death represents not just the end of the universe as we know it, but also the fulfillment of the natural laws that govern all cosmic systems. It is the consequence of the second law of thermodynamics, which ensures that all energy is eventually spread evenly across the universe. As this process unfolds, the universe will continue to expand, cooling and stretching over an unimaginable period of time. The stars that once lit the sky will no longer shine, and the once dominant forces of gravity and nuclear interactions will no longer have any role to play. The universe will have reached the end of its journey, and the forces that once created galaxies, stars, and life will have dissolved into nothingness. The universe will be left in a state of total stillness where no processes of creation or destruction occur. The final stage of the universe's evolution, this state of heat death is not just a point in the future, but the inevitable outcome of all that has come before. The birth of stars, the formation of galaxies, and the rise of life were all part of a natural process that has been driven by the forces of gravity, thermodynamics, and quantum mechanics. But all processes have their limits. The heat death marks the culmination of the universe's expansion, the point at which everything that once existed will fade away into the darkness. No more stars will form, no more galaxies will collide, and no new structures will arise. The universe, once full of light, motion, and energy, will have become a dark, cold, and silent void devoid of life and activity. It will be the ultimate stillness, the final chapter in the cosmic story that began with the Big Bang. As we approach this distant future, it is clear that the end of the universe is not a sudden event, but the slow, inevitable conclusion of the forces that have shaped the cosmos for billions of years. The stars will burn out, the galaxies will drift apart, and the remnants of the universe's former activity will be scattered across the void. The final moment will be marked by absolute entropy, when the last traces of energy fade away and the universe exists in a state of perfect equilibrium. In this final stillness, time will lose its meaning and the universe will have reached its ultimate end. As the universe continues its inevitable march toward its final moments, the last vestiges of activity slowly fade into the cold, expanding void. The forces that once shaped the cosmos, gravity, nuclear reactions, dark energy, will no longer be capable of sustaining the processes that once brought life, motion, and creation to the universe. The final stage of the universe's existence, often referred to as the heat death, is the ultimate consequence of its ongoing expansion and the increase in entropy. With no more stars being born, no new galaxies colliding, and the black holes evaporating over time, the universe will lose the dynamic energy that has defined it for eons. The universe will gradually become a place where no change occurs, where no events unfold, and where the passage of time becomes meaningless. This end will not come in a burst of sudden destruction, but in a quiet, inexorable fade into stillness. At this point, the universe will consist only of the faint remnants of its once vibrant activity, tiny particles of matter scattered across an infinite void. The last remnants of energy will be stretched thin and will no longer be capable of supporting any processes of creation or destruction. The temperature of the universe will be incredibly low, approaching absolute zero, as all the thermal energy that once fueled stars, galaxies, and the formation of new matter will have dissipated. The remaining particles will be isolated from one another by the vast distances of space, and the universe will be devoid of any interaction or meaningful motion. In this state of absolute entropy, the fundamental forces that shape the universe will have exhausted their influence, and nothing will remain but the ghostly remnants of the cosmic processes that once defined existence. The cosmic background radiation which has lingered since the early moments of the universe will become almost imperceptible as it too is stretched to the point of invisibility by the continued expansion of space. This radiation, once a vital trace of the universe's infancy, will no longer be detectable by instruments, as its energy is so diluted that it can no longer be perceived. This marks the final stage of the universe's journey, from the explosive birth of the cosmos to the quiet end of all activity. The universe will have evolved from a dense hot singularity to a vast expanse of cold, dark space. All matter will have been spread thin, and all sources of energy will be exhausted. In the absence of stars and galaxies, the universe will remain a dark, cold place. No light will shine and no cosmic events will take place. The once bright stars that illuminated the universe will have all burned out, leaving only the cold remnants of their former selves. White dwarfs, neutron stars, and black holes, though remaining for an incredibly long time, will eventually cease to exist. The radiation from dying stars and the lingering presence of black holes will gradually dissipate over unimaginable timescales, eventually leaving behind no trace of their once mighty existence. The final particles of matter, which will be spread out across the void, will be incapable of interacting, forming new structures, or creating new life. The expansion of the universe driven by dark energy will continue, but it will no longer be able to create new structures or facilitate the birth of new stars. Galaxies will drift farther and farther apart, eventually becoming isolated from one another, and the once dominant structures of the cosmos will dissolve into isolation. The energy once available to fuel the birth of stars, galaxies, and planets will be so thinly spread that no significant processes will remain. As the energy of the universe becomes more evenly distributed and entropy continues to rise, the universe will become a place where no change occurs. It will be a place of perfect stillness, where no physical processes or life can exist. Time, once marked by the birth and death of stars, galaxies, and civilizations, will lose its meaning in a universe where nothing changes. The end of the universe in this state of perfect entropy represents the final chapter in the cosmic story. It is the inevitable conclusion to a process that began with the Big Bang, when the universe emerged from a singularity and began expanding. For billions of years, the universe has evolved with stars forming, burning through their fuel, and dying galaxies colliding and merging, and the forces of gravity and dark energy shaping the cosmos. But all things must come to an end. The universe, once full of life and activity, will fade into darkness, where no new structures will form, no new events will occur, and no new life will arise. The heat death of the universe marks the end of all physical processes, the ultimate consequence of the expansion and the relentless increase of entropy. Yet even in this final stage, the universe will bear witness to the passage of time. The laws of physics will still apply, but their effects will no longer be meaningful. The universe will be frozen in a state of stillness and no new events will unfold. The end of the universe is not a dramatic event. It is a gradual decline into a state of perfect equilibrium where everything has been spread out and no more changes can occur. It is the final result of the forces that have shaped the universe since the beginning: gravity, dark energy, and entropy. The universe will become a place where nothing moves, nothing evolves, and nothing changes. The forces that once shaped the cosmos will have run their course, and the universe will have completed its journey from birth to death. In this final stillness, the universe will exist as a faint memory of its once vibrant past, a place where no light shines and no energy remains. The passage of time will continue, but there will be no events to mark it. The heat death of the universe represents not just the end of the universe's physical existence, but the end of everything that once mattered. The stars, the galaxies, the planets, and the life that once flourished. all will have faded into the darkness, leaving behind only the memory of a once-living, ever-expanding universe. Though this end is distant, the inevitable fate of the universe is clear. The forces that shape the cosmos, the birth of stars, the formation of galaxies, the expansion of space, will ultimately lead to the slow, inevitable decline into darkness. The universe will fade and time will lose its meaning. The universe once filled with light, life and activity will become a cold, dark and empty place, marked only by the faintest traces of its past. The end of everything is not sudden, but a gradual, irreversible decline into stillness and entropy.